Good morning, all. Today's class, unit number 3, lecture number 4. So, on burn rate, governing equations, and area relationship related to a solid propellant rocket motor. So, last three classes, we could discuss on the basic principle of a solid propellant rocket engine and the hardware components and the important propellants what we are using and what are the important parameters, factors to be considered for the selection of the propellant and different design structures can be used for the propellant system, solid propellant rocket systems, and performance related to the burning mechanisms, combustion, and the related topics were discussed in the last class. So in today's class, we are going to discuss on burn rate and the important governing equations related to burn rate of your rocket propulsion solid rocket motor and the area relationship with respect to that of the solid propellant rocket. So let us the outline of the lecture. Today's lectures are first one is a burn rate. The second one, the factors influencing the burn rate. The third one, the burn rate law. And the fourth one topic is governing equation. And the last topic, what we are going to discuss today is the area relationship of your solid propellant rocket motor system. Coming to the first concept, burn rate. So burn rate is nothing but, as you know, the burn rate is nothing but the rate at which the propellant is the surface is consumed. So as you know, the solid propellant normally the surface reaction on the surface area, the burning takes place with respect to the surface area consumption of the propellant. That amount of burning takes place. The burning may be of three types: progressive burning, regressive burning, and what is other one more type of burning? Can anyone answer? Progressive, regressive, and one more. What is the other type of burning? And can anyone answer for the question? Are you there?
Yes, sir.
What is the other type of burning? Regressive, progressive, and the third one. Anyone? Don't know. So the third one is neutral burning. So we have neutral burning, regressive burning, and progressive burning of the solid propellant with respect to the time. That burning may be classified in the three categories. So compared to that case, we have the three different burning processes: solid, progressive, regressive, and neutral burning. With respect to the solid propellant on the surface proportional surface area, the rate at which with the period of time, the rate at which the propellant burning on the surface, which is exposed to the surface burning, that is the amount is consumed. That is called as the propellant burn rate. So propellant burn is nothing but the rate at which the propellant burn rate is nothing but the rate at which the exposed propellant surface is consumed. So it is measured at a distance normal to the surface of the propellant consumed in a given time. So that is nothing but the measurement of a distance normal to the surface of the propellant, solid propellant consumed in a given particular time. That's why it is a rate at which the propellant burn, the rate at which the propellant burn, the rate at which the solid propellant burn with the surface propellant consumption. That is called as the burn rate. So normally, the burning surface of the rocket propellant grain resides in direction perpendicular to its burning surface. As we know, of course, whenever the propellant is consumption, due to the consumption, there will be that burning surface will be get decreased, and the surface area it resides. So the grain resides in a direction. That reduction in the burning area of the surface of this grain will be taken place. That direction is perpendicular to the burning surface. So normally the rate of regression or the regression rate or burning rate. So burn rate is, as I told earlier, the burning may be of three different types: progressive burning, regressive burning, and neutral burning. If you go for considering the rate of regression, so regression rate is nothing but the rate of regression is typically measured, or burn rate is typically measured in inches per second or millimeter per second is also known as the burn rate or burning rate. So it is millimeter per second, somewhat related to the velocity of the same as that of the velocity of flow of any fluid surfaces. So coming to this solid propellant consumption, how much amount of the propellant surfaces resides in the grain surface reside in the direction perpendicular to the direction of the surface is known as the burn rate. The time duration, for a particular duration of the time period, how much propellant of the solid propellant is consumed in the surface of the propellant is consumed with respect to time period is known as burn rate or burning rate or regression rate Regression is nothing but the time with respect to receding with respect to or decreasing the burning with respect to the that surface perpendicular direction of the flow, perpendicular direction of the surface for a particular time duration is known as regressive burning. So the rate correspond to the receding grain structure or a decreasing manner is known as regression rate, and burning rate or burn rate is measured in terms of millimeter per second or centimeter per second or in terms of inches per second. So that is the base of your burn rate. So burn rate are also determined in subscale firing. The firing we have, for example, whenever the solid propellant or the grain structures is loaded in a solid propellant rocket motor. So we have, as you know, if you want to generate thrust, we need to provide a nozzle at the end of the chamber. So what are the three components of the, what are the major three components of a solid propellant rocket motor? Can anyone answer for the question? What are the three different, what are the major components of a solid propellant rocket motor? Answer the question. Different or major components of a solid propellant rocket motor.
Combustion chamber nozzle.
I didn't get you. What is the first
No.
component?
Combustion chamber nozzle.
Combustion chamber or nozzle. Only two components is enough. Huh? To generate thrust.
No, sir, one more.
Start from the first component. What is the first arrangement? What is the first component in the rocket motor?
Igniter.
Okay, start with the igniter, ignition system, igniter, then propellant grain, then chamber, and then nozzle. Okay, so we got to initiate the combustion of the propellant. Further, we need propellant. Propellant is inside the motor casing. So we have one casing kind of thing. The casing acts as a chamber. Inside the chamber or casing only, we are loading the solid propellant grain structures. And igniter is meant for igniting purpose, ignition systems. So once ignition starts or combustion starts, we have to expand the gases through a system known as a nozzle. So that will be tends to give a thrust at the end of the system. So that is a major component. So whenever you are burning in the subscale firing of your solid propellant rocket or solid propellants, the firing motors with different slices can be used. So we have, if you have the branded is option as a function of the different chamber pressures. So from the nozzle chamber area to the nozzle exit, with respect to nozzle throat section, if you are varying the size of the throat, different sizes of the throat, so burn rate is function obtained as a function of different chamber pressures. So whenever the ignition starts, the chamber pressure and chamber temperature also reacts majorly to have the burn rate concept. So that's why the major important parameter which will define, which will describe, or which will give the idea about the burn rate is the chamber pressure. So if you maintain or if you are varying the different throat sizes of a chamber along with the nozzle, that burn rate will be obtained as a function of different chamber pressures. So it is normally burn rate we have to give in terms of a normal representation or in correlation or equations. Normally it is an empirical representation and does not address any complex thermodynamic law combustion processes. So we'll be having one equation. That equation is also known as the burn rate law, or that is correspond to only correlation is known as is all are empirical representation. It's not like a complex thermochemical or combustion process equation. It will give representation majorly on the parameter known as chamber pressure. So burn rate is major dependent on the chamber pressure. So that is the thing in the given in this under this topic. So what are the factors influencing burn rate? So coming to the burn rate influences, how the burn rate will get affected or will get enhanced. So what are the factors to be considered, or what are the factors will be acting on the burn rate operation or burn rate applications? Or the propellant burn rate is influenced by the first one, as I told earlier, very important parameter of the burn rate is combustion chamber pressure. So chamber pressure of the combustion chamber is the major performance parameter or factor which will define the burn rate. Similarly, initial temperature of the propellant grain. So if you want to initiate the process, if you want to start the ignition, so the propellant temperature grain has to have some temperatures. So if you maintain the proper, or if you are achieving the if you are achieving the optimum or required initial temperature of the grain, that tends to give the burn rate effectively. Similarly, the velocity of the gases, as I told earlier, whenever the combustion gas is in combusted, the gases has to flow through the nozzle. So the gases flowing through the nozzle, that we have to consider the gases combustion of the gases velocity, or the combustion gases velocity flowing to the surface, burning surface, that also affecting the burn rate. Then next one is the local static pressure acting on the each and every location of the system. That is known as local static pressure. Last one, the motor acceleration and spin. So whenever if you go for accelerating the motor of the casing, the rotation of the casing or acceleration of the casing or acceleration of motor, that is nothing but the chamber. That will be also a cause for the, is also a factor of the burning rate affection. Of course, we have once we have the chamber pressure, obviously the chamber temperature also one of the important parameter of the factors which influencing the burn rate. So the important factors influencing burn rates are chamber pressure, initial temperature of the grain, velocity of the combustion gases, local static pressure, motor acceleration, and the spin. So these are all the some important factors which influence the burning rate of the solid propellant rocket. So how to modify, or how to enhance, or how to change the burning rate, how to enhance the burning rate. So with these are all the parameters. If you are varying these parameters, we can able to modify or we can able to enhance the burning rate or regression rate. So what you would do is decrease the oxidizer particle size. As you know, if you want to combust gases, whenever the fuel in term added with the oxidizer is a form of propellant, so oxidizer is the major important parameter which will enhance the burning. So if your the particle size of the oxidizer is very small, if you are changing or decreasing the size of the particle, so that we can increase or we have effectively enhanced the burning. Also, hence we can enhance the burning rate of the solid propellant rocket. So, for an example, if you want to increase or reduce the percentage oxidizer, so if you have the greater oxidizer fuel ratio, that tends to give achieve the burning rate with respect to our requirement. So, as well, if you want to increase burn rate, we want to add a catalyst or energetic particles or suppressant. If you want to control the, or if you want to reduce the burning rate, you want to add suppressant. If you want to enhance the process, you want to add a catalyst. Same as this, decrease or increase the percentage oxidizer. Here also you want to, catalyst can be added or suppressant can be added. So if you add, that will enhance or you can decrease the burning rate. So then you want to go for the lower or higher, if with respect to the cell pressure or with respect to burning rate obtaining cases. So the pressure also can be lower or it can be higher. So with respect to the chamber pressure condition, we can able to modify the burn rate. So modification in the burn rate can be depends upon the size of the particle of the oxidizer fuel ratio, and chamber pressure condition lowering or increasing or higher or lower value of the pressure of the chamber, and adding the catalyst or a suppressant. We can add it or we can add suppressant to control the combustion so that we can able to achieve the required combustion process, and we can able to make the enhance or modifying the burn rate of the solid propellant rocket system. So what are the catalysts? As we told earlier, we can have some adding some catalysts. These are the catalysts are mostly added to enhance the process. Normally we need to add only enhancement of the process. So these are normally we are adding only catalyst. So these are all example for the catalyst like ferric oxides, copper oxides, manganese dioxides, and aluminum percompound. So if you are using AP based composite propellants, then we have to use this kind of propellant catalyst can be added as to enhance the burn rate. Ferric oxides, copper oxide, manganese oxide, or camel used in AP based ammonium perchlorate based composite propellants. If you go for ammonium nitrate based mixes, AN based mixes, there you have to add potassium dichromate or ammonium dichromates. Similarly, if you are using cane sugar propellants, potassium nitrate sugar propellants, their potassium nitrate case, potassium nitrate we are using, then we would add ferric oxide or ferric iron sulfate and potassium dichromate for the adding as the catalyst or enhancing the bond rate thing. So sometimes we are using a lamp life carbon, they may be slightly increase the burn rate. So this can be due to the reason of the heat transfer of three mode conduction, convection, radiation from the combustion flame to the propellant surfaces. So these are all the catalysts can be used to enhance. Our objective is always used to enhance the burn rate. So if you want to enhance the burn rate, we can able to add, we can add this kind of catalyst. Other than that, the other catalysts also can be added. So these are all some example. The catalyst can be used with respect to this ammonium perchlorate, ammonium nitrate and potassium nitrate, and we combine with sugar propellants. These are the propellants if you are using. We can able to add. We can add this catalyst to enhance the burn rate. Next one is very important topic is burn rate law. So, what are the factors affecting the burn rate? Anyone? Can anyone answer? What are the
Static,
factors affecting the burn rate of the solid propellant rockets?
static pressure, combustion chamber pressure, um, temperatures,
Yeah,
and
major is
altitude.
first one is the combustion chamber pressure. That's a major parameter. Second one is the local static pressure. Okay, then answer is fuel ratio also an important parameter which will affect, and chamber temperature also one parameter. The rotation of the motor and the spin or orientation of the motor, that also one important parameter. So these are all parameters. So with respect to that factors influencing, we can able to have one law. That law is known as the burn rate law, given by Saint Roberts. It's called the Saint Roberts law. It's given the idea about burn rate or B suffix. B suffix denotes burn, or denotes rate. If you can use simply R also fine. You can simply use R as the burn rate. So R equal to A into PC power N, where PC is nothing but the important factor which will influence the burn rate is chamber pressure. So PC is nothing but the chamber pressure, and the A here given is nothing but a burn rate coefficient, and N is nothing but burn rate exponent. So it's also known as pressure exponent. So N is nothing but is index. N is the index, or it is the index correspond to the pressure. That's chamber pressure. That's when it's called as, hence it is called as pressure exponent or index. N is the index or pressure exponent or burn rate exponent. So A is the burn rate coefficient A. So as I told earlier, the unit is in terms of millimeter per second, or centimeter per second, or meter per second, or inches per second. So the burn rate law is relation between the burn rate R and the chamber pressure PC. So as we discussed, in the normal to direction of the flow of the surface of the burn rate, so the burn rate is always perpendicular to the direction of the surface of the burning. So with respect to time period, with respect to chamber pressure. So R equal to given by is proportional to the chamber pressure. It's a very important factor affecting the burn rate. So with respect to pressure of the chamber, we can able to have equating with respect to A. A is nothing but a burn rate coefficient. Is a coefficient correspond for the equation of the burn rate, and P is chamber pressure. So N is the index. N is always is in the terms of 0.05 to 2 inches per second. The typical values of N is not typical value of N. So typical value of N is the value of 0.05 to 2 inches. So R is the burn rate. A is the coefficient. So if you know the coefficient, if you know the index value correspond to any particular reaction or in combustion, we can able to define, or we can able to identify, or we can able to determine the burn rate R. So R is sufficient if you know the value of A, and if you know the value of the N index correspond for the reaction. So you can able to identify R value, or you can able to identify PC, vice versa. So like that, this is a law. The major law is governing is known as Saint Robert's burn law. So this the diagram is in the present, the graphical between the natural logarithmic of the chamber pressure with respect to the natural logarithm of the depression rate. So from that we can able to identify the slope. The slope is nothing but n. The slope n gives the idea about what is the index. So of the reaction, the equation, the line curve equation of this line curve is R equal to A PC power n. So R equal to A into PC power n. That is nothing but the curve equation. So from this slope, if you are planting the logarithmic value of two different variables x and y, you can able to identify the slope. If you want to for an example, if you want to calculate the slope of any curve, so what you want to do is you want to plant the graph between x and y and logarithm, taking logarithm. So taking natural logarithm of that values and plot the curve between x and y, log of x and log of y, then you may able to get one line like straight line like this linear line. So from the linear line, you can able to get the value of the slope n. So that is a normal procedure is where we are following in the mathematics. So the point of intersection of this curve on this line, that is called as the values with the ln of a. So that is nothing intercept. So intercept lies nothing but ln of a. The where the slope n is nothing but slope. N will be given is the slope. So y equal to mx plus c. If we go for that equation, from that we can able to find m. Here also from this equation we can able to identify the value of small n, lateral logarithm of A. So line A can be given the idea about what is the value of A. The slope will give the idea about what is the slope of the A. Of that equation or the relation reaction with respect to different pressures. So if you are burning a propellant at different pressures, we can able to achieve different regression rate. So from that we can able to identify what is the current equation, how that it varies. So from the able we can able to identify whenever the regression rate increases, the burn rate also or regression rate or burn rate also increases. So this is the inference from the idea that will give the idea about the burn rate law given by Sand Roberts. So here you can able to see we have one radius, initial radius and final radius of the port. So port is nothing but the grain structure or the grain port. It is a grain port, or we can say. So whenever the it is gets ignited, due to that the surface area getting burned. So due to the surface area burning of that burning surface along the length of the chamber, so the burning surface area only getting burned. So due to that, the radius will vary initial to final radius. So if you have the time duration for a time duration of that time duration, the dimension of the initial and final will give the idea about the burn rate. How much changes in occurs from the burning initial surface to the burning at the final surface. The changes in the burning surface with respect to that of the time is nothing but burn rate. So all can be find out experimentally after burning or before burning, the surface area changes with respect to the direction of the flow, so direction of the burning surface. So that is the idea about the burn rate. So all can be found surface area dimensional change, or can be found experimentally from the initial and final surface area burning dimensional change. So if you want to calculate the burning rate, burn rate or refresh rate, so if you have the initial port diameter or initial diameter of the port is available in terms of radius. So after burning, we can take the burned product out and we can measure three different or five or six different cross sectional. We can measure the dimension and take the average of that one. That will give an idea about the final port dimension. So that difference between the final port diameter to that of the initial port diameter will give the idea about with respect to time period is nothing but burn rate. So R can be found between the difference in the radius or difference in dimension to that of the burning time. That is called as burn rate. So R regression rate. So one more parameter and one more data, one more this is given is web distance. So propellant distance, also known as the propellant web, is nothing but is defined as the linear amount of the propellant consumed as measured normal to the local burn surface. That's why I told you between the time period of 0 to burning time TB. So if you are with respect within that area time period from 0 to TB, how much amount, what is the achievement of the R for a duration of time T dt? That is nothing but web distance. It is called as propellant web. So propellant web or propellant web distance is nothing but this a linear amount of the propellant consumption as measured normal to the local burn surface is known as burn rate. Is known as burn rate web. Is known as web distance or web propellant. So, as I told earlier, the performance of the solid propellant rocket motor depends on the propellant burn or exposed propellant grain surface area, nozzle throat area, nozzle exit area, amount of energy in the propellant tends to give the thrust at the end. The performance of the propellant depends on the propellant burn rate. Expand first one also depends. So that's the first one is the propellant burn rate. Second one is the export propellant grain surface area. Third one nozzle throat area and exit area. And the fifth one, last one is the amount of energy in the propellant, the amount of heat energy generated. That is the performance or thrust of the rocket motor. If you want to calculate ISP, if you want to calculate the thrust value, so these are the parameter will affect it. It will depends. First parameter depends is propellant burn rate. Second parameter defined is this exposed propellant grain surface area. Third one is nozzle throat area and nozzle exit area, amount of energy in the propellant. So that we discussed last class, the different types of burning. So again, I want discussing again, going to discuss again, progressive burning, neutral burning, regressive burning. The burn surface area increases with time, progressive. Burn surface area remains relatively constant with time, neutral burning. Progressive burning, burn surface area decreases with time, that is regressive. You can able to identify from the diagram very easily with respect to time correspond to the pressure of the or pressure or thrust. We can simply say thrust or temperature. So if it is increasing manner, it is a progressive. It is an almost constant, it is a neutral. If it is in decreasing manner, it is aggressive. So these are all the three different types of burning with respect to the burn rate, with respect to the thrust acting to that of the time. So depends on the time, we can able to define three different burning: progressive burning, neutral burning, and aggressive burning. So next is the topic is important governing equation related to the solid propellant rocket motor system. So as we know, the rate of change of mass, the mass changes in a chamber is equal to the difference between the mass entering the chamber and mass leaving the throttle. So from the chamber, we have allowing certain amount of masses. From the mass chamber, it will be leaving through the throttle. So when we go, if we go for finding what is the mass rate, the control equation again, that is mass exiting or max nozzle exit is equal to mass flow rate out is equal to PC80 by C star. Again, already we have the formula P of the chamber, A of the throat divided by C star. What is C star here? Can anyone? C star?
Characteristic velocity.
Hmm?
Characteristic velocity.
Yeah,
Correct.
characteristic velocity. A throat is throat area. Chamber pressure is peace chamber. So the normal conjugation m dot out is equal to exit to the nozzle. What is the amount of nozzle exit is equal to m dot chamber into A throat by C star. So this we already discussed in your unit number one. Second one is the conservation of mass principle. The change in the mass of the chamber, dm chamber by dt is equal to mass in minus mass out. So mass, what is mass in? So we are allowing certain amount of propellant, and propellant gets burned in a burning surface area. So tends to have one burn rate. So rho AB, so equal to rho AV. Continue question again. So A burning, A burning, burning surface area, and RB burn rate, rho is the density of the propellant. So that minus what is this was out is equal to PC80 by C star. So difference between these two will nothing but the change in the mass inside the chamber with respect to time period dt. M in my M out is equal to M in is equal to rho density of the propellant or burn rate and A burn. That's why I told you it is almost equal to rho AV. Here AV almost equal to is equivalent to the R burn rate. A is the burning surface area again area density as obviously it is a density only. So mass exit is equal to P chamber A observed exit by C star. So according to that basic law, as you know, the perfect gas law related to the solid propellant law again, as same concept, M equal to PVRT by or PV equal to MRT. So using the same formula, PV equal to MRT, where M bar equal to where P is the chamber pressure, V is the volume, what is the volume of the chamber, R is the, what is R of the gas, if it is a gas. So T is the chamber temperature, what is M bar, capital M bar,
Molecular mass of the gas.
yes, correct, perfect. Molecular mass of the particular gases. So this is a basic relation, basic perfect gas law, M equal to PV equal to MRT. So that only here written here, PV equal to MRT. So these are all the relation can be used while designing or while designing a solid propellant rocket performance or designing a rocket system. So coming to the equilibrium conditions, whenever the operations are on equilibrium, as you know, obviously energy in equal to energy out. So we are balancing same thing. R equal to R again R into rho into AB. So here R in writing in terms of APC raised to M. So same thing only. R replaced by APCM. So A into P chamber N into rho density of the propellant into burn area or burning surface area or AB is equal to P chamber in the A rod by C star. So using the relation, you can able to get the value P chamber is equal to P chamber chamber pressure is equal to where my cross multiply everything A into rho propellant into A burn into C star divided by A throat. The whole power. Already we have N is available. So using the relation, you can able to identify P power chamber equal to 1 by 1 minus N. So using that common equation, these all related concept, you can able to identify solid propellant rocket motor chamber pressure is equal to A propellant A burn C star by A throat power 1 by 1 minus N. So if you are rearranging, you may able to get the answer. So similarly, go for the index n equal less than 1, n equal to more than 1. If n is less than 1, it is the explosive combination. N is more than 1, it is explosive. So typical value of n will be between 0.2 to 0.6. So these are all value always you should know. So then coming to the conservation of mass principle, again same principle. Rate of gas generation is equal to change of propellant mass plus nozzle flow. So this is the energy inequality energy out again. Mass energy, sorry, conservation masses in, masses out. So using the relation A B R B rho P d by dt of rho 0 V 0 plus A T P 0 rho P 0 root of gamma by T 0 by 2 by comma plus 1. The same formula we already had in unit number 1. Nozzle exhaust velocity case. So rho AV, rho in the area and the V. So velocity of the nozzle. So this is the entire term denotes velocity of the nozzle in the area and density. So here also velocity again mass flow rate rho B A B R rho in the A in the V. So A equal to V equal to R here, A equal to A, rho is rho. So change of propellant mass is d by dt of the propellant masses between the density and volume. So rho 0 V 0. So using the concept, you can able to get what is the value of AB by AT area ratio. So AB by AT can be given. AB by AT given. You are rearranging all these things. You can able to identify AB by AT equal to K is equal to in terms of if you are rearranging and simplifying, you can able to get the answer. P0 by RBAB, rho B root of gamma into 2 by gamma plus 1, the whole power gamma plus 1 by gamma minus 1 by root of RT0. Again, if you are rearranging it, R equal to APC line. So you are substituting for R equal to A into PC power N. P0 here is P0. P0 is nothing but PC. PC and P0 also same. So P0 it will be stagnation pressure, same pressure as always using air breathing or rocket propulsion. The same thing here also same thing. P0 is nothing but chamber pressure that is equal to stagnation. Sorry, stagnation pressure of the chamber that is equal to PC. So if you are substituting R equal to A PC raised to N, so A will be here as is PC here, PC power N or PC power C0 power N. PC or PC power both are same. So here you have N, here you have 1. So it will be 1 minus 1 by 1 minus N. P0 power N or PC power N. Use it P0 or PC, both are same. So using all these things, you may able to get one equation. So go for the approximation. If you approximate equal to that one, P0 approximate equal to AB by 80 power 1 by N, that is also equal to K power 1 by 1 minus N. So from the relation, after approximation of this concept, we can able to get the ratio for the area ratio AB by 8 equal to K equal to P0 power 1 by 1 PC power 1 minus N into A into rho B into C star power 1 by 1 minus N. So you see the all previous this and this relations, you can able to get K is equal to AB by 80 is equal to P0 power 1 minus N into A rho B C star the whole power 1 minus N. So from there you can able to add. If you want to get this P0, you can rearrange some other way, the same formula only, both are same only. So this is in terms of KB by 80, this is in terms of P0. That's all. So P0 equal to K power 1 by 1 minus K is nothing but AB by 80 or AB by 80 power 1 by 1 minus N into A into rho B into C star. So these are equation has to be can be used while designing or while discussing on the propellant performance of the solid again. It will be useful for solving numerical. So the formula has to be remember. You have to remember is the two formula is very important to remember. So K in terms of AB by T P0 1 minus N into A rho P C star power 1 minus N. So same formula written in terms of real in terms of P0. So if you want to find P0, you would use this relation. So you remember this formula. Only one this formula is very important to remember. If you understand, if you know the formula, you can able to design the rocket motor performance. So this is based on the approximation. If you go for exactly the area ratio, you have to substitute the value of gamma or everything, and you can use it. So you can use the anyway. Both the way you can able to get the result. So the simplified expression can be used to get the performance of the rocket of the solid rocket motor. You can able to identify AB by 80. You can able to find burning surface area if you know the AT value. If you know the ATAB, you can able to identify P0. So everything depends upon the location. So if you want to find the PC, same person at any location, you can able to use the formula at any location. So AB at any location, AT is AT only, it won't be changed. So location, what is the variable is A is constant, density is constant, C star correspond to the relation, there is no changes. N also we can it will be given for the particular reaction. Only variable here is burning surface area and the pressure. Pressure vary, burning surface area vary. Similarly, burning surface area vary, pressure will vary. So with respect to that, we can able to get the performance of a designing of a rocket equation or rocket for any reactions. So the reaction only define the variations. So other thing will be constant for the particular reaction. A is for one reaction, N is also for the particular reaction. So N will be always between 0.2 to zero point 0.6 value for any solid propellant rocket application. So with respect to, you can able to get the you can able to design a rocket motor, or you can able to identify the performance of the rocket motors. So what are things you have to remember is mass continued equation, conservation of mass principle, amount of mass in and amount of mass out with respect to the solid rocket motor. So amount of in is available, amount of out is available. If you can able to go for amount of in, amount of out, so you can able to identify the same. The same thing only given here. You see, this is the same equation here also. Both are same. Same AB by AT, propellant A through DAC star, P chamber 1 by 1 minus n. The same thing only here also. KS would AB by AT, P0 1 minus 1, AB rho C star 1 minus n. So here you can use 0. It is the Steinmetz process, that's why using here as 0. So if you have confusion, you can make it as PC. Simply keep it as PC for everywhere. PC everywhere. PC air pressure, PC general pressure like that. So there won't be any confusion. Okay, these are all about the important bond rate concept of the bond rate of the solid propellant rocket motor and the factors affecting the bond rate case and important governing equation respect to the solid propellant rocket motor and the area ratio correspond to solid rocket motor, so that they can able to design a rocket motor, and as well you can able to identify the performance of a solid propellant rocket motor.